Hi everyone, my name is Neha Kardam, and in this lecture we are going to learn about IC specifications and simple interfacing. So let's get started. So these are the topics which we will be covering in this lecture. We will be covering logic levels, noise margin, and then interfacing families of ICs, other specifications, MOS and CMOS ICs, interfacing with switches, interfacing with LEDs, interfacing with buzzers, relays, motors, and solenoids. And then we'll be covering interfacing using an opto isolator, and then current sourcing and sinking. So let's start with logic levels and noise margin. So as you know, in digital electronics, the voltage characteristics, they are defined by two logic levels, which are 0 and 1. 0 is for low level and logic 1 is for high. So these are the two logic levels that we work in digital electronics. Now in digital electronics we have the noise also. Noise also comes into picture when we deal with these logic numbers. So let's read here. It says noise immunity or noise margin. It is basically the logic circuit's insensitivity or resistance to undesirable voltages, and that is called your noise. In another word, you can also say that noise margin is a peak amount of noise voltage that may be superimposed on a weak gate output voltage. So let's see one of the example. So we have this TTL voltage profile chart you see here. This is the input characteristics you see, and this is the output characteristics. So you see the low level is from 0 to this G and D is the ground, so which means from 0 to 0.8 volts, and the high signal which can be sent, it will be sent in between 2.0 to 5.5 volts. Okay, so which means if you have any signal which is less than 0.8, that can be easily passed through the input side of the TTL, and it will be considered as low logic. Okay, and if you have any signal, for example 3.2 is passing, so that can pass through this, and it will be considered as logic high, and anything in between them, between 0.8 and 2.0 will be your undefined region. And same here, you have at the output characteristics. So this is the output range for the TTL. It is from 0 to 0.4 volts. So it's typically 0.1 volts, and the high range is 2.4 to 5.4 volts. So it can output voltage between 0 to 0.4 and between this range. So anything in between is your undefined region. So you see that the tolerable range for output signals levels are narrower than for input signal levels, and to ensure that any TTL gate which is outputting a digital signal into the input of another TTL gate will transmit voltages which is acceptable to the receiving gate. So now here the difference between the tolerable output and input ranges is basically called your noise margin of the gate. So you can calculate the noise margin for TTL. So for example, if you compare let's compare the low level noise margin, which means we will going to we are going to subtract this 0.8 from 0.8 from 0.4, and if you do that, then you will have 0.4, and that will be your low level noise margin. And if you subtract here in the high level, then you have 2, you have 2 here, the minimum is 2, and here minimum is 2.4. So if you subtract these two, you will have 0.4, and that 0.4 is basically your high level noise margin. So that's how you can calculate the noise margin for both the levels. Now let's move on to the next slide. It says an input voltage of 0.2 volt to a TTL, so which is powered at 5 volts, would be interpreted as a logic 0 or logic 1. So if you remember that the minimum input voltage which can be accepted by the TTL is from 0 to 0.8. So this 0.2 comes under 0.8, which means it is under low logic. So this is going to be your 0 or low. Now next is input voltage of 3.5 volts to a TTL IC, and 5 volt power supply is given, so that would be interpreted as a logic what. So you have to see the range. So this is 3.5, and the input range starts from 2 volts, so it is definitely above 2 volts, which means this is going to be 1 or high. And let's see the third. It says a typical high output for a TTL IC powered by 5 volts might be about, so here it is talking about the high level output. Okay, so we saw like input voltage and output voltage range. So here it is talking about the output voltage range, and in that too it is talking about the high output voltage range. So a typical high output for a TTL IC might be about, so your answer would be, it's going to be 3.5. So these two options are given. This is going to be the low. So among these two we have 3.5. It's going to be logic high. Now last question, we have a logic circuit's insensitivity or resistance to undesirable voltages is called noise, and it's called noise and is also called noise margin or noise clutter. So it's definitely called a noise margin, so that's our answer. So now let's see input voltage profiles, TTL and 400 series CMOS. So here there are two comparisons have been made. For one is for TTL, another is for CMOS. So you can see this is the range for input voltage profile for TTL. From 40% to 100% is for high, and for low is 0 to around like 25%, whereas CMOS has a low voltage profile, low input voltage profile, typically higher than the TTL, and the high voltage profile is smaller in range when compared with the TTL. So let's see. So right now it is connected, it was connected to low, and in that case, if that happens, if this logic probe is connected to your low, then you see this this button will be turned on, which will show low. Or for CMOS it's going to be between 0 to 3 volts, and for TTL it's going to be between 0 to 0.8 volts. Now see what's going to happen next. So anything is between low and high is going to be your undefined. So you see this region and then this region, which is for CMOS it is from 3 volts to 7 volts, and for TTL it's 0.8 to 2 volts. So anything between these two range is undefined, and that's what you can see here. So this the green button you see, which is brighten up right now, is for low logic, and the red one is for the high logic. So if you have both of them, if both of them are bright, or they are like going back and forth, on and off together, then that means you are in the undefined. Your TTL is in the voltage is in the undefined region. So that's why you have this here, both of them brighten up. Undefined logic probe reading may vary depending on manufacturer also. So like for this particular case which we are taking, it has just two buttons to show undefined, but then sometimes the logic probe may have like one more button which may indicate the undefined region or undefined logic, if you have if you came across that point. Now next is the high. If the logic probe touches the high region, if it is in this region, then this this button will be turned red, and it will show the high logic. And the high logic for CMOS, it is from 7 volts to 10 volts, and for TTL it is from 2 volts. So here it is 2 volts to 5 volts. So you can see in CMOS you have like a higher range, whereas the maximum range you have in the TTL is 5 volts. So now here a caution, output voltage profile differs other families voltage profile. So that's what I told you, like CMOS and TTL, they have like different output voltage profile. It is just for 5 volts, and CMOS has for 10 volts, and there are many under these also which may vary in readings. Now let's do a quiz quickly. So here we have a question which says an inexpensive handheld instrument called a logic probe or oscillator is commonly used to check logic levels in TTL or CMOS circuits. So what's going to be answer in that case? Obviously it's going to be logic probe. So we have here answer logic probe, and because it is very handy, handheld. However, these days oscilloscopes have also come which are handy in nature, but for these particular application we use logic probe. Now an input voltage of 1 volt to a CMOS IC power supply is 10 volts would be interpreted as a high or low or undefined input. So 1 volt will come under low voltage or low voltage profile, because it lies under the range of the CMOS input voltage, which is from 0 to 1.5. So that's why this is a low input voltage. Now here's the thing, so as I said, like 1.5 low voltage profile for CMOS. So sometimes it varies in book wise also, like in some of the books you may find this rating as 1.5 or 3 volts, something like that. So don't get confused, just see like what CMOS you are particularly referring to. So yeah, if it is a 1 volts input voltage going in, then it is definitely going to be a low it's going to be a low logic. Now next, third, we have an input voltage of 5 volts to a CMOS IC. 10 volts power supply would be interpreted as a low, high or undefined. So this is going to be undefined, because 5 volts does not lie in between either in low or high voltage profile. So this is going to be undefined. Now next we have an input voltage of 9 volts to a CMOS IC powered by 10 volts would be interpreted as a high, because 9 volts is pretty close to 10 volts and it is lying into the high voltage profile. So that's why we have high here. Now let's see. So TTL voltage profile. So another quiz. You see here it's from ground to 0.8 volts for low voltage and 2 volts to 5 volts for high in case of input voltage profile, and for the output is from 2.4 volts to 5 volts, and low is from ground to 0.4 volts. Okay, so now input you are having is of 4 volts, and then what is going to be the output? So you see the 4 volts, this is going to lie in this high range between 2 volts and 5 volts, so your output is going to be high. Now we have 0.3 volts which is lying between ground and 0.8 volts, so this is going to be low. So that's why you have low here. And then what will happen if you have 1.2 volts? So 1.2 volts is between 0.8 volts and 2 volts. So something over here. And this region is not defined. So this is going to be undefined region. Now, next is 2.2 volts. So this is again above 2 volts. So your output here is going to be high. Now we have low voltage CMOS ICs, and it says so lower voltage CMOS ICs, they are used in many modern designs such as small portable electronic devices. Several low voltage CMOS IC families are available using 3.3 volts logic instead of 5 volts power used by 7400 series TTL or 74HC00 series CMOS ICs. So example for that would be a 3.3 volts CMOS, which include the 74 low voltage CMOS and 74 ALVC, which is advanced low voltage CMOS series ICs. And there is one more example, which is 1.8 volts CMOS, which include the 74 advanced ultra low voltage CMOS series of ICs. So here there are two important factors that have led the IC industry to move towards lower power supply voltages in CMOS devices, and they are, first is so if you cut down the power supply voltage, then the power dissipation will reduce dynamically. In fact, it will reduce more than proportionally, so which is huge. And the second reason is that as the industry has moved towards even smaller components, the CMOS transistors gate and its source and its drain is getting even thinner, and thus incapable of insulating, voltage potentials as high as 5 volts, and that's why we have like such a low voltage CMOS these days in the market. Now let's move on to the quiz. Now let's see. Oops. Okay, so we have 74HC00 series of CMOS ICs operate on a 5 volt DC power supply. Is it true and false? So answer is already there, so which means this is true. And then second, we have 74 advanced low voltage C00 series of CMOS ICs operate on a 3.3 volts or 10 volts DC power supply. So if you remember that how CMOS ICs, they have become smaller in size, and their voltage levels have also decreased. So 3.3 is going to be the answer. Now next we have 74 advanced ultra low voltage series of CMOS ICs operate on a 1.8 volts or 5 volts DC power supply. So this is also 74 advanced ultra series CMOS. They also work at a very low voltage. So the answer is going to be 1.8 volts. The next is TTL to CMOS interfacing. So before we get into detail of TTL to CMOS interfacing, it is important to know the output and the input levels of both for the TTL and CMOS. So here you see the output standard TTL levels voltage profile is given for output voltage profile, and here is the input voltage profile for CMOS. So you can see the voltage level, the output voltage level is from 0 to 0.8 and then from 2.4 to 5 volts, whereas for CMOS is from ground 0 to 1.5, and then higher side is from 3.5 to 5 volts. So if you see the voltage and these current for profile also, so you can see for higher is 400 microamps and this is 16 milliamp, and then for CMOS it's 1 microamp, and same is for CMOS. So if you see the voltage and current profile, you see that the output drive circuits for the TTL are more than adequate to drive the CMOS inputs. Which you can see just looking at these different voltage levels, and you see that the voltage profile, however, it do not match, but yeah, TTL it is more adequate to drive the CMOS. And the low outputs from the TTL, they are compatible, because if you see that they fit within the wider low input band on the CMOS side. So you see from 0 to 0.8 it can easily fit into CMOS, and there is a range of possible high outputs from TTL IC is from 2.4 to 5 volts, whereas for CMOS it's from 3.5 to 5 volts. So you see that this high voltage, it do not fit within the high range of the CMOS IC. So this incompatibility could cause problems. So these problem you see because of this incompatibility, they can be resolved by using the pull-up resistor between the gates to pull the high output of the standard TTL up closer to 5 volts. And a complete circuit for interfacing the standard TTL to CMOS is basically, you can see here, and you see that here the 1 kilo ohm pull-up resistor has been used. And this circuit basically is driving either 400 series or 74 HCO or FACT series of CMOS ICs. So you can see how with the help of pull-up resistor the incompatibility which was caused can be avoided. Now we are going to move on to the next TTL. We are continuing the TTL to CMOS interfacing. So I'm gonna quickly read these. Interfacing is a design of circuitry between devices. So interface circuitry shifts levels of voltage and currents for compatibility. So we already saw that. TTL and CMOS high and low voltage profiles are different. So that too we saw in the previous slide. So current requirements for TTL and CMOS are different. So example here is the same example has been taken here. So this is your TTL, this is your CMOS, and 1 kilo ohm pull-up resistor has been taken, and it is tied to the supply. So design notes, output current of TTL okay to drive CMOS device. Output voltage profile does not fit CMOS input voltage profile. So use pull-up resistor as interface device to adjust the voltage profile. So in the previous like most of the things in this slide is similar to what we covered in the last slide, but my purpose of putting up the last slide is that so that you can actually see the voltage levels and then make prediction that what is wrong if we do the interface. So if looking at the voltage level, you know that like higher voltage doesn't match, and that could be the problem while interfacing these two devices. So so now I'm going to move on to the next slide. So this is quiz. Let's see, it says the design of circuitry that translates voltages and currents between devices such as between TTL and CMOS is called boundary scanning or interfacing. So definitely this is interfacing. Now next is interface circuitry shifts level of current and voltage, time and temperature. So these are the four options which are given over here for compatibility between two devices or circuits. So we have to put here current and voltage because we never discussed about the time and temperature. So that is something, those are the external factors. So for interfacing, only current and voltage profiles or these labels are important. Now next question is in TTL to CMOS interfacing, pull-up or a temperature sensitive resistor is used to shift voltage levels. So we saw that we use the pull-up resistor in while doing the interface. So the answer is going to be pull-up resistor. And the last question is the voltage profile for TTL and CMOS are they same or different? So we saw that it was different, so the answer is going to be different. So now next we have CMOS to TTL interfacing. So till now we saw TTL to CMOS interfacing, so this is just opposite. And in the previous one we know that we use pull-up resistors, but from CMOS to TTL interfacing is little different. So CMOS ICs, they can drive low voltage TTL, or they can drive like ultra low or advanced low power Schottky TTLs inputs, but most CMOS, they cannot drive standard TTL inputs without special interfacing. So manufacturers, they have made interfacing easier by designing special buffers and other interface chips for designers. And for that, the one example would be the use of 4050 non-inverting buffer, which we are going to see. So before we see that, let's go through these key points. Interfacing is the design of circuitry between devices. Interface circuitry shifts levels of current and voltage for compatibility. So this second point is pretty clear, that we need a compatibility, because we already saw the current and voltage profiles were different. So CMOS and TTL voltage profiles are different, the same thing. Current requirements for CMOS and TTL are different. So CMOS like 4050 IC, which is a CMOS buffer that can be used as a interfacing device, and that allows the CMOS inverter to have enough drive current to operate up to even 2 standard TTL inputs. And there's another CMOS ICs, which is 74SCT00 series of CMOS, which is widely used when interfacing between NMOS device and CMOS. And the NMOS output characteristics, they are almost same as LS TTL. So this NMOS is if you have studied semiconductor devices, so I hope you know what it stands for. And now we're going to see this design notes. It says output voltage profile of CMOS is okay to drive TTL inputs. Output currents from CMOS is not enough to drive standard TTL. Use special purpose CMOS buffer IC to adjust the current levels. So we saw that we need a CMOS buffer for interfacing from CMOS to TTL. Now let's quickly see some of the questions here. The design of circuitry to make TTL to CMOS or CMOS to TTL connection is called interfacing. And then we have TTL and CMOS voltage profiles. They are same or different? They are different. So, and then we have TTL and CMOS current input requirements and output drive compatibilities. They are also different. And then we have interfacing. Standard TTL to CMOS involves using buffer or pull-up resistance between the input TTL and CMOS devices. So here it's talking about interfacing standard TTL to CMOS. So if it is TTL to CMOS, then we will be using pull-up resistors, and if it was opposite, then it would be your buffer, CMOS buffer. So pull-up resistor. Now other digital IC specifications we're going to see. So we have drive capabilities. This is sometimes referred to as a fan in or fan out. So if you see a bipolar transistor, it has maximum wattage and collector current ratings. So these ratings, they determine the drive capabilities. So drive capability in case of a digital in case of digital ICs is called its fan out. So if you see those in data sheet, those are your like voltage and current ratings. All this stuff is your drive capabilities. And now next is fan out. It says number of inputs of a logic family that can be driven by a single output. The drive capability of outputs is called your fan out. So in another word, we can say that if the fan out of a standard TTL gate is, for example, 10, then it means that the output of a single gate can drive up to 10 inputs of the gates in the same subfamily. So typically the fan out value for a standard TTL ICs, if you search, then you will find it will be 10, and the fan out for low voltage, low power Schottky TTLs, the short term for that is LSTTL, is 20, and for 400 series CMOS it is considered to be about 50. So you see like how the fan out levels, the number of inputs for a logic family, how they have increased, and they have like they are different for each of them. For a standard TTL IC it's 10, and for low power Schottky TTL they are 20, and for 400 series CMOS it is 50. Now next we have fan in. So fan in, it is the load an input places on an output. So it is pretty simple by the definition. And then we have a propagation delay, and this propagation delay has to do with the speed of the logic element. Lower propagation delays means higher speed, which is a desirable characteristics. So you see here, if you want to have a high speed IC, so for that you need to have lower propagation delay, and if the propagation delays increases, then the speed of the IC goes down. So you will see propagation delays more in the timing diagrams, and there are numbers actually, like how much delays are there in the speed of the IC. So for a standard TTL, it has like propagation delay of about 10 nanoseconds when compared with a propagation delay of about uh, between 30 to 50 nanoseconds for a 400 series CMOS IC. So the 400 series CMOS IC, however, that would consume around like really low power of about 0.001 milliwatt. While on the other hand, the TTL gate that may consume more power, around like 10 milli watt of power. So you can see the power consumption in CMOS is so small when compared with the power consumption in TTL, and the propagation delay is also different for both of them. So now next we have power dissipation. So power dissipation is generally as propagation delays decreases, the power consumption and heat generation increases. So you see, if your power delay is low, so power consumption and heat generation it will increase. CMOS is noted for low power consumption, so that we already discussed. Now let's move on to the quiz. So first question says uh, the fan out or quantum equivalence refers to the drive capability of the outputs of a digital IC. So here we are going to have fan out. We never discussed about quantum equivalence. Now next is faster digital ICs are desirable characteristics, have higher or lower propagation delays. So we learned that if the speed is high, in that situation we need to have lower propagation delays or decreased propagation delays. So the answer should be lower here. Now third is the CMOS or TTL family of digital ICs is known for its very low power consumption and is commonly used in battery powered products. So we learned that CMOS CMOS has very low power consumption. It was 0.001 milliwatt, whereas for TTL it was 10 milliwatt. So definitely it's going to be the CMOS. Now, a few more questions. The drive capability of logic device outputs is sometimes called, is it fan in or fan out? It is the number of inputs of a logic family that can be driven by a single output. So we learned that this definition belongs to fan out. So the answer is fan out. And then we have CMOS devices that are noted for their extremely high or low power consumptions. So this question is similar to the last question we saw in the previous, I guess in the previous slide. So here we know that CMOS has lower power consumption. So this is going to be low. And then next we have a logic device with a low propagation delay would be considered to be a high or low speed device. So let's read it again. It says a logic device with low propagation delay. So if you have low propagation delay, then in that situation you are going to have high speed, because the propagation delay and the speed, they are inversely proportional to each other. So the answer is high. And next is several desirable characteristics of logic devices are good drive capabilities, so low power consumption and high or low propagation delays. So if you note here, it says several desirable characteristics of logic devices. They are good drive capabilities, low power consumption, and here it's going to be low propagation delay, because we want a low propagation delay in order to get the higher speed. So that's our desirable characteristic. So the answer would be low. Now next is MOS and CMOS ICs. So we are going to learn about these. So MOSFET, which you might have studied in semiconductor class, that MOSFET forms the main component in MOS ICs, which is metal oxide semiconductor. Let me So MOS stands for metal oxide semiconductor, and because of the simplicity of the MOS ICs, they uses less space on a silicon chip, and therefore more functions per chip are typical in MOS devices than compared to TTL. And also because of the packaging density on the chip, like they are so close together, and therefore because of such a nice design, the size of the chip is very small. So this MOS technology is widely used in large scale integration, and even in VLSI, which is very large scale integration devices. In microprocessor they are used, in memory chips they are used, in clock chips they are used, typically fabricated using the MOS technology. So let's see, in MOS you have these PMOS, NMOS, and CMOS. So these are the three technologies used to manufacture ICs and TTL. So this is another very fast technology. So here is a important thing to note down here, that previously CMOS was basically slower than compared to TTL. But the more recent CMOS families, such as 74AC00 and 74AL VC00 series feature, they have very low propagation delays. So which means they have a very fast speed. They are high speed digital circuits, and they have the propagation delay is drastically low. It's between 2 to 5 nanoseconds. Now let's see next. So this NMOS is basically, it stands for negative channel metal oxide semiconductor. NMOS ICs are faster than PMOS ICs, where PMOS ICs stands for positive channel metal oxide semiconductor. Um, and and then this CMOS, it stands for complementary metal oxide semiconductor. Both PMOS and NMOS devices are used its manufacture. So these CMOS ICs, if we see the cost wise, they are very low, and they are simple in design. They dissipate less heat. They have good fan out. So if you remember, in previous slides we discussed that the fan out for CMOS uh, 400 series was about 50, which was huge when compared to the standard TTL, which was 10. And they have like good noise margin also, and some low voltage CMOS, they can supply as low as 1.7 volts. So that's really small voltage, which means the IC is going to be also very, very small. So they have lower power consumption, and that's what made the CMOS ICs more popular when compared to TTL. Now let's see, we have CMOS ICs are noted for exceptionally lower power consumption, so it's the same thing. CMOS ICs were lower than bipolar digital ICs, such as TTL devices. And then transmission gates, or bilateral switches, are unique digital devices created using CMOS technology. Now let's do some quick quiz. So the MOS part of CMOS stands for metal oxide semiconductor, which is a technology used in producing ICs with high or low power requirements. So it's going to be low power requirements because that's the desirable requirement. Okay, and next is PMOS, NMOS, CMOS are three technologies that use FET, which is field effect transistor, to fabricate a modern digital IC? So answer to this is going to be true. So CMOS, NMOS, and PMOS, these technologies, they do use FETs to fabricate modern digital ICs. And then last we have a CMOS, stands for negative channel metal oxide semiconductor, and is a part of extremely high speed, high power consumption digital IC. So that's a no-no. This is false, because CMOS stands for complementary metal oxide semiconductor, and it has low power consumption, not extremely high. So this is false. So there are more topics which we have to cover. So those I'm going to cover in the next lecture. So this was the last topic for this lecture. So thank you so much for watching.